I'm Michal. I'm from RIT, and I'll be talking to you about aesthetic inference for smart mobile devices. Oh, sorry. Yes. Um, and so briefly, so I'll first introduce and sort of modify the problem. Then I'll tell you a little bit about the methodology, about the model, the training procedure. Then I'll show you some of the results. And then I'll get to the conclusion. So over the last 15 years, we saw a huge development in technologies. In 2002, one of the first cell phones with a camera was a Nokia 7650, which had a 0.4 megapixel camera with amazing 4 megabytes of memory, internal storage, where today we got to 12 megapixel cameras in iPhone X or Google Pixel 2 with hundreds of gigabytes in internal storage. And so now it comes to several problems. So in the last few years, we saw that cell phones have become sort of the one of the major media by which we construct or capture our images. And so we run into two problems, either memory management or sort of management of the pictures. So with the exponential increase in the number of images and the popularity of portable devices, we studied the performance of resource-constrained models on various design various design choices in their effect on image aesthetic ranking. We study particularly two problems: aesthetic inference and image cropping, of which I'll tell you a bit about. So basically, our main goal was to study how the varying input size and the depth of the layers, which control the complexity of the models, affected the performance of our models in binary classification, image ranking, and image cropping. And so these are the main contributions, which I'll get to later. So basically, what we did for the different models with the different design choices, we utilized a Siamese network structure when then we applied a multi-stage loss, which consisted of a regression loss, a ranking loss, and a difference loss, where in regression loss you were basically just trying to optimize for predicting the ground truth score. In the ranking loss, you were trying to optimize the ranking of the images, and the difference was you basically you would try to predict the average score of the images and then predict their differences. We evaluated our models in two datasets. First, the the EVA dataset, which is the current standard dataset in evaluating aesthetic algorithms, and the FCDB dataset, the flicker cropping dataset, which has been actually introduced last year at WACV. So first, I'll tell you briefly about aesthetic inference. So we report two metrics. One is the Spearman's rank order correlation, and then the overall binary accuracy on the EVA dataset, where even though EVA dataset has continuous scores, you basically binarize the scores by taking the scores that are above 5 to be high scores and below 5 to be low scores. So now quickly to results. So basically, I show that the bottom MobileNet 224 model, 224 1.0, sort of achieves near state-of-the-art accuracy. So the best models are actually comparable to previous state-of-the-art. Then to the right, I sort of show how the rank order correlation changes with the different design choices. I can expand that in the poster. Here is basically the plot, a log linear plot of the performance of the rank order correlation versus the number of operations you perform in the network. And so we can actually see it's pretty log linear. I have 30 seconds. Well, okay, so we get to image cropping. Basically, I use the different models as proxy functions to pick the best crops. I show here that we achieve very good results, especially compared to other aesthetic-based rankers, which are the first and the second models at the top. Here are some examples, and I have 10 seconds. Thank you so much. So we basically show that the combination of losses achieves very good results. And if you have any more information, please stop by